Alright, so in this discussion I'm going to go over ventilation considerations and internal loads. So we'll go over the fresh air requirements for commercial buildings. There's actually code that specifies certain amounts of fresh air per person. And we'll go over that and go over that calculation. And then go over a few ways that you can supply fresh air in a building. So there are some options here, some more energy efficient than others, and then we'll actually look at some HVAC sizing considerations as well. So first of all, you need fresh air in a building. You need to get rid of contaminants. You need to get rid of the carbon dioxide that builds up because people are exhaling. There are standards that dictate this. You want to jot down ASHRAE in case you haven't already. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers, and they propagate all manner of standards. So this is just a small snippet of standards. There's a lot more. We're not going to get into all of them in this class, but we will get into a couple. The one that that deals with commercial indoor air quality is 62.1-2019 or 62.1-2019, it's commonly known as. The ventilation standards for residential is 62.2, you can see down here 62.2-2019. And these were recently updated 2019 and accepted even past 2019. So these are very updated standards. So this tells you how much fresh air you need in commercial buildings. You are free to look at the document from ASHRAE. You can actually view it for free online, and you'll see that it is well over 100 pages long. So as with most things, the codes and standards are pretty complex. So we're going to stick to the basic stuff here that indicates how much fresh air you need in a commercial building. So there's a few things that this depends on. This is the formula here. So the airflow rate. So this is the formula that tells you how many cubic feet per minute are required in a space. Okay, so this is cubic feet per minute, and you'll get practice with this in your lab this week. So it's a pretty simple formula actually. It's just the area. Okay, so the RP, which is the outdoor, basically a CFM per person times the number of people at maximum occupancy, okay, plus the CFM per square foot times the square foot. It's pretty straightforward actually. You just have to find these factors. There's only 4 variables in this equation, and that'll give you your total CFM that's required when the occupancy is at a certain level. So this can vary, just to be clear. You can vary the ventilation by using dampers and variable frequency drives and so forth. You can sort of throttle back fans and make them go faster and so forth, because you don't want to be providing ventilation all the time if you don't have to. So you want to provide the minimum amount necessary, because remember, with ventilation you're bringing in outside air. So if that outside air is cold, you have to heat it up. If that outside air is warm, you have to cool it down. And so there are a number of means by which you can sort of modulate, kind of get the ventilation to go up and down. But we'll just, for now, what we're going to do is look at how much ventilation is required based on a certain capacity of people. Okay, so let's just do here. So I have 1,000 square foot office space, and I need to know how many cubic feet per minute of fresh air do I need to provide at full occupancy according to 62.1-2019. Sorry for the typo there. So 62.1-2019. Okay, so we need to find all of these variables, and we can go to ASHRAE to do this. So I'm going to go to a different screen here in a second. Okay, so here is the full ASHRAE standards and guidelines. You can see you can access these all for free online. So let's access 62.2-2019. Here it is. Right, and so let's go to these tables here. Okay, so you'll do this in your lab today. So here's your table. You can see we have all of our variables. We have our CFM per person, or R sub P. We have our outdoor air rate, or R sub A. And then we actually have our maximum occupant density as well. And so let's look for, over here, we'll look for office. We can find it. going office. Okay, so we have office space, right? So our R sub P is 5, so that's CFM per person. Okay, our CFM per square foot is 0.06, and then and our occupant density is 5 per 1,000 square feet. Okay, so let's go back to our presentation here. I can find it. Okay. Okay, so now we have all our variables, and we just plug and play. Okay, so 5 CFM per person, we know it's 5 people per 1,000 square feet. We have 1,000 square feet, so the total occupancy there is going to be 5 people. 0.06 CFM per square foot, and then 1,000 square feet. Plug them in, and you get 5 times 5 plus 0.06 times 1,000, and you get 85 CFM. So that tells you how many CFM cubic feet you need to add when this is in when it has full occupancy. So when you size your HVAC system and your ventilation system, you have to you plan for this ahead of time, and you would say, okay, this is 1,000 square foot office space, and so I'm going to need to have up to this much ventilation for this room. Okay, so when you design your ventilation system, you have to have at least 85 CFM, so you'd probably put in 100 CFM just to be safe, because if the occupancy changes, then you're going to have to add more, and so forth. Okay, so let's do a different use. So you have a 1,000 foot train station, 1,000 square foot train station. Everything else is the same. How much fresh air do you need to provide? So I'm not going to go back to that table, but if you go to the table in ASHRAE, it's 7 CFM per person in a train station, and the occupancy is 100 person per 1,000 square foot. The R sub Z is 0.06, so that's the same. Okay, so we plug that in, and about 5 times 100 plus 0.06 times 1,000. So you can see the difference here. We need to plan this ahead of time. If we are providing the ventilation for a building, we have to know how many people are going to be using it, how big it is, and what it's being used for. If it's office space, 85 CFM, the exact same size for a train station, something that's a higher density of people, you're going to need 560. So you think about it like a train station, you have crowded people in there, so you need more ventilation overall, and that's what this factor adjusts for. Okay, so you need to consider that when you design your ventilation system. So how do we provide ventilation? There's any number of ways. A really common way in a lot of commercial buildings is through what's called a rooftop unit, often called a packaged unit. This was actually in a previous presentation, but I'll go over this again. This is something that's it's basically like an air conditioner all in one. So instead of a split system, you have an air conditioner. You can have a heater in here. They usually do have a heater. You can see here's sort of a schematic here. But the important part for our purposes here is the ventilation, right? So this provides heating and cooling. Okay, in here there's a filter in there, give you a little bit of help here. So there's return air that comes in a return duct. Okay, flows into this unit, and then it's either heated or cooled, and then provided back to the building. This here, these louvers. And should be a damper here that will open and close. That allows fresh air to come in. Okay, so if it needs full fresh air, those dampers will open all the way up and pull the fresh air in. If you don't need any fresh air at the time, let's say there's nobody in the building, and the sensors know that, you can actually close these and just recirculate the air and not use any outdoor air. But this is a really common way to get ventilation in a commercial building. Now the problem is, again, you're just grabbing this outdoor air. So if it's cold outside, you have to heat it up in here. If it's hot outside, you have to cool it down. If it's humid, you have to dehumidify it. So it's not. You have an energy penalty, and the energy penalty, so to speak, is given by this equation, the sensible heat equation. So the sensible heat equation is, and this was actually in last week's lesson, it's at 1.08 times CFM times delta T. So if you want to know how much you need to heat up or cool down, or how much energy you need to either add to air to heat it up to a proper temperature, or how much heat you need to remove to drop it down to appropriate temperature. You use this sensible heat equation. Okay, so that's cubic feet per minute of outside air, and then the difference between the indoor and the outdoor air, and times 1.08. Okay, so it's actually, again, pretty straightforward equation. Let's just do an example here. So if we provide a 560 CFM of fresh air, right, so from same as the train station in the previous problem, how much heat do I need to add to the air if you want to get the indoor air to a 65-degree temperature and it is 45 degrees outside? Okay, so it's a pretty simple plug-and-play equation here. So we have our CFM is the air coming in. We have our delta T, the difference between the inside and the outside is 20 degrees, so we need to warm it up 20 degrees, and then times 1.08, and it's really that simple. So 1.08 times 560 CFM times that delta T, and so in order to warm this air that is now 45 degrees, to warm it up to 65, okay, assuming you're bringing in 560 CFM, cubic feet per minute, you're going to need to add 12,000 BTUs per hour of heat to that air in order to heat it up. Okay, and then you could do it if it was 45 in, I don't know, just let's say it was 85 outside and you want to cool it down to 65, you would have to remove 12,096 BTUs per hour. Okay, and that's it. At that temperature, you'd have to constantly remove that much heat at that rate. So there are alternatives to rooftop units. One of them, and there was a video and a description in this week's lesson called an ERV and an HRV. What these do is they remove, basically they exchange heat from the outgoing and ingoing air without those air streams actually touching each other, and they do that through a heat exchanger. So what these do is they basically even out the temperature. So let's say in this image here we have fresh air from the outside. Okay, so this is warm air coming in. Then we have we're in the cooling season, right? It's hot outside, so we have cold air. This is the cold air from the inside. So normally what we do is we exhaust this cold air and just blow it right out and bring the warm air in, and then we have to cool down that warm air with an air conditioner. But with an ERV, what happens is the cool airstream goes through, there's a couple different ways to do this, but basically it goes through a heat exchanger. Okay, and it's like these fins that sort of touch, it's metal that touches, so the air itself doesn't touch, just the metal does. Okay, and so you have cool air that's being exhausted, but we want to keep, like, we want that air to be cool, so we'd rather bring in cool air instead of this hot air. So what we do is we take the cool air out, and as it crosses through this heat exchanger, it actually pulls this cool airstream, pulls heat from that hot air that's coming in before it is exhausted. So this cold air, which we want it to be cool, we want to keep this cool air. Instead of just ejecting it outside, what we do is we basically warm it up. We pull some heat from that incoming air and reject it outside, and then the air that comes in that was hot and humid actually cools down and is a little dehumidified. So it actually comes in cooler than it would otherwise. Okay, so that's the principle of an ERV. So an HRV only absorbs heat, whereas an ERV absorbs heat and moisture. So there are different ways. There's membranes in here that you can use. You can use this this wheel. It's literally a wheel that spins around really slowly, and that both absorbs the heat and the moisture and sort of evens it all out. And this is, again, this is your air coming in, that's your air going out. So the whole intent here is we have this cool air inside when when it's hot outside, and we have to bring in fresh air, but we don't want to bring in the heat in the fresh air. So what we do is we basically pull heat and dump it into that air that's going out, and cool the air down. What's really nice about these is that it automatically works the opposite way during the heating season. So if we have hot air inside and cold air outside, like we don't want to bring that cold air in and have to heat it up. So what happens is this warm air, when it crosses the stream with the cold air, because of the second law of thermodynamics, the heat will go into that cold air that's coming in, and then it preheats the air, which makes it more efficient. Okay, so these units can have transfer efficiencies of up to 75%, so they can be really good in terms of saving energy. Another way to reduce your energy, your cooling load, is through what's called an economizer, or free cooling. So as it turns out, in commercial buildings in particular, even when it's cold out, because you have so many internal loads, like a lot of people and electronics and computers and whatever, it's actually not uncommon that, like, if it's cold outside, you're actually still cooling inside because there's so much heat being generated by all the people and all the activity and all the equipment and so forth. So think about it, if it's cold outside and I need to cool the inside, it's a lot easier just to run a fan and bring in cold outside air than to cool down the air actively, right? So like what you can do is you can have your RTU, or whatever, your air handler, and you have cooling coils in here, right? So instead of, you can deactivate the cooling coils and just bring in fresh air that's cold, and it's free cooling. That's why it's called free cooling, right? So all you need to do is run a fan, which is a lot less energy intensive than running a compressor to run a cooling coil. Okay, so that's called an economizer free cooling. Again, this is all, you got to program it, and you have to sense the outdoor versus the indoor temperature, and you have to be really careful about this. But there is a lot of opportunity for this. As you might imagine, the further north you go, the more opportunities you have. So this is this is from the EnergyStar.gov, and it shows you the approximate number of hours of free cooling available across North America. And you can see up here is like you can use 8,000 hours of free cooling, which is a lot. Even in Florida, you can use thousands of hours of free cooling. So like overnight, it still drops down. It can drop down and be cool enough where you can use that free cooling. So that's an economizer. So moving on to HVAC sizing. This is something that we have not addressed yet, but heat pumps and central air units and air conditioners are rated in tons. A ton is 12,000 BTUs of either heat added, 12,000 BTUs per hour of heat added or heat removed. Right. So a 1 ton of heating means you can add 12,000 BTUs per hour of heat. 1 ton of cooling means you can cool 12,000 BTUs per hour out of the building. And so all the multiples are pretty easy, right? So 4 ton is 12,000 times 4, which is 48, 4.5 ton. These come in half tons, so you'll go like 1, 1.5, 2, 2.5, and so on. And just incidentally, if you're ever looking on a nameplate on a heat pump or an air conditioner, you'll usually see a multiple of, if you see a multiple of 12 like this, like it says 36 right here, or if it says 48, or if it says 54, which is would be 4.5 tons. Yeah, 4.5 tons. It's in the model number, just so you know. So it's really straightforward. If I want to calculate the tonnage, it's a really easy equation. So at that train station, needs about 12,096 BTUs per hour to heat. How many tons of heating would this require? So it's really easy. 12,096 divided by 12,000. You need 1.008. Well, we can round that one down to 1 ton, but normally you would round up to the nearest half ton. Here's another example. On a really cold day, the train station would lose about 28,000 BTUs per hour. How many tons of heating would it need, rounding to the nearest ton? Okay, so this is like maybe on the 90s, the 1% day or the 3% design temperature day. It needs 28,000 BTUs per hour. So 28,000 divided by 12,000, 2.33. Round that up to 2.5 ton. So you need a 2.5 ton unit to accommodate that. So there's a couple other considerations to make with internal loads. As I mentioned before, there's a lot of loads inside of a building that can heat it up. So people emit heat, anything that's using energy emits heat. Any electronics, all of the electricity, just about all the electricity ends up as heat inside the building. Lights, computers, motors, cell phone chargers, TVs, it doesn't matter. And so this can actually make a really big difference in terms of sizing your HVAC system. Again, we need to size the HVAC system to keep it at the comfortable temperature. Well, in the summer, in the heating season, you have heat that's trying to get in through the building shell and building envelope, but you also have all these internal loads that's adding heat to the building, and so your HVAC system has to compensate for that. And it can add up to quite a bit. So the average person emits about 250 BTU per hour, and they can go up. If you're doing something more active, you can go up to 400, 500 BTU per hour. But 250 is about a good average. So if I have 10 people inside of a building, assuming 250 BTUs per hour per person, how many BTUs per hour are they emitting? Really easy. 10 people times 250 BTU per hour is 2,500 BTUs per hour. So what if I have 500 watts combined of computers and lights and electronics and a 250 watt projector in a room? So how many BTUs per hour would that be? I'm going to let you figure that one out. You'll do in your lab this week. But all of these can add up to quite a bit. And we can use the sizing of our HVAC system to approximate our seasonal heating and cooling loads. So to this point, we've been using HDD. We also kind of mentioned CDD, the HDD times the area times the U times 24, right, to do the seasonal heating load. But we can also approximate it using the capacity of the equipment, assuming that the equipment is sized correctly. In order to do that, we just need a couple of things. We really only need the capacity and what's called the equivalent full load heating hours, or the equivalent full load cooling hours. And you can see the equations down here. So the annual cooling load, really straightforward. It's just the equivalent full load cooling hours times the capacity of the equipment. And the equivalent full load cooling hours, it's a way to approximate the equivalent amount of time a cooling system would have to run at full capacity. And that's really all it is. So you're not running, you have a 5-ton cooling unit. You're not going to run it at 5 tons all the time. Like, it's not running 24/7. In some applications, some buildings, you might run it half the time. That's a really high load, but it's going to be generally lower than 50%. And so what you can do is you can, based on where you are, so the climate that you're in and the building use, there are acceptable numbers for these equivalent full load hours. And once you have that, you just multiply it times the capacity, and that'll give you a good approximation of how much heating and cooling is needed. So let's do an example. So what's the annual heating load for a 4-ton heat pump of a grocery store in Wilmington, Delaware? Okay, so first of all, we need the capacity, which is in BTUs per hour. So that's 4 tons. 4 tons, and 1 ton is 12,000 BTUs per hour, right? So that's 48,000 BTUs per hour. Pretty easy. So now we need these equivalent full load heating hours. In order to do that, we need to look it up. Okay. So here is a chart from the Mid-Atlantic Technical Reference Manual, which is a kind of an industry standard manual. And you can see our equivalent full load heating hours. We're in Wilmington, Delaware. We have a grocery store, so it's 1,015. Okay, so that's our equivalent full load. So what that's saying is, over the course of the heating season, you would operate your equipment at about the equivalent of 1,015 hours. That might be, full load for half a day and partial load for part of the time, but the total is going to be 1,015 total hours of full load. Okay, so now we just plug it in. right? So we just plug it in, 1,015 times 48,000, and we get 48,720,000, or 48.72 MMBTU. Okay, so that's a way that you can approximate a heating load. You can do the same thing for cooling load, and you'll actually do that in your lab this week. Okay, and that's it for this presentation.